So now let's look into a bit more detail of into the concept that is covered in this workflow. So the first thing we want to look at is this concept called discretization, right? What does that mean? So the whole idea is that we want to break up any regular shape into regular bits. Like, for example, if you look at the Harbor Bridge, I'll be using that example many times. The Harbor Bridge has a very sort of non-standard or non-straightforward up and down shape. You got a curvy bit at the top, right? When you need to deal with a curve, it's always a bit difficult than dealing with a straight line or straight bar, for example. So, by using this discretization method, we want to be able to chop up this curve into smaller parts where individual bits are regular shaped. For example, a rectangle or a triangle. Right? In your calculus, especially your differential calculus, if you chop a curve into smaller and smaller bits, you can start to approximate those smaller bits with a linear shape, right? So if you divide by the model body into an equivalent system of many smaller body, you can work out the mechanics on those smaller parts using your linear equations. But then you also need to bring them back together to make a big body, right? So you need to make sure when you divide those bits, you have points that allow them to connect back. So this is what it means by interconnected at points that are common to two or more bodies. And those interconnected points is what we call the nodal points, right? So for example, if you chop a bar into two pieces, right, the point where they join in the middle here on my fingertip is what we call a nodal point, right? That's what happens in a line. But if you have a shape, for example, if I have two shapes and I join together, not only I have 2 points up and down here, but I also have a line joining between them. So that becomes a boundary line, as I said here, joining the two discretized parts. But this thing can also go further if you have two 3D objects at the point they join, like my two feet, you join together on a surface, right? There's a surface of joining between the two discretized parts, and that's what I said here. This could be also joined together by the surface, right? So, what are the possible choice of finite elements, right? What's the possible choice to chop up a bigger pieces of irregular shape? Well, we live in 3-dimensional world, so the natural thing to think about is we have 1-dimensional system where everything is just a line. And the language of finite element analysis, they call them beams, right? Beams. And you can have 2-dimensional shape, like triangles and rectangle are the most common choice. And you can see the most common choice of the nodes are at the apexes of these 2D shapes. And you move further to 3-dimensional case, you can have tetrahedron, hexahedron, or pentahedron, depending on what's the best way, most suitable for the shape you have at hand. Okay, as I said, the most common choice is to put the nodal point at the corners of all these shapes, right? This is what's shown in the top. But you can also choose additional node in your element, as shown in the bottom line here, where they put an additional node in the middle of all these line elements, right? You can see on the beam, there's one in the middle. At each one of the 3 edges of the triangle, it has an extra node, right? if you put more nodes in, you will have finer control of the force distribution over your whole structures, and you will get a more accurate description of what happened when your structure is put into external load. But of course, that also increases the associated computational cost to solve the problem, right? Now, once you have these finite elements or these features being set up, right? I draw all the nodes, right? I draw all this shape, and I decided I put X amount of nodes on these elements. I need to solve for the features involved, right? And typically what we do here now is try to obtain a set of algebraic equations to solve for some unknown quantity, right? As I said many times, that unknown quantity is most likely to be the displacement of your structure when it's put under loads, right? For example, if I put this triangle, I put a load in this top bit, what's the corresponding displacement of each node there, right? So that's the primary things I'm interested to solve in the finite element analysis, right? But I can also solve for some secondary quantities, right? For example, if I put a force at this top bit of the triangle, and all these points will deform, right? And I can work out the displacement. From there, I can also work out what's the corresponding forces that are experienced by these 2 points where I only put a load at the top, right? So, to solve the forces on these 2 points, you need to know their displacement first, right? So that's why the force or the stress are called secondary quantity, because you need to work it out based on something else, right? As I said, we are dealing with a situation, or most of the cases we'll be dealing with in this course are linear problems. So everything obey Hooke's law, right? F equal to minus kx, right? So basically what we try to do in the above 2 lines is first figure out what this k is for the structure we are interested in. F is what we've been given, the external load, and we want to solve these questions by finding out, to find out what X is, right? So this is basically what this whole thing is about, right? To put this into a more visual context, if, for example, we start with an object that looks like this, right? The discretization process will chop this up into individual elements that perhaps look like 3 triangles, simplest case. Now, if I down there, I find out there are 1, 2, 3, 4, 5 nodes on these structures, right? With these 5 nodes, on each node, I want to work out what's the displacement where some forces being applied to one of the nodes, typically, right? So if I apply, say, a force or some loading at this point, all the other points will deform a little bit. So I want to work out what that displacement will be and how that will affect the stress on all the other points, right? If the displacement are too large across the whole structure, there's dangers that the whole object might collapse when I put the load on. And that's the things I try to look out for in the real design. So if we look at some real example, now this is what you will see in your lab. You'll see, for example, in the one-dimensional case, you will have all this beam building a framework, and you can see that, you know, the red bit are the point where they withheld a lot of loading, and the blue bit is the part that are not holding that much load. So you can expect if this structure have this kind of loading, then this part of the structure will have a lot of deformation, right? So the idea is somehow maybe in your design process you want to redistribute all the loading so the whole thing look more or less evenly distributed, right? You can also have things in two-dimensional case, and as you can see here, they divided this irregular shape with circle inside into different triangles, right? That's the process of discretizing a 2D structure. And you can move on to more complex materials such as this three-dimensional component in machinery, where you have probably using some triangle elements to simulate the rounded part, where more elongated triangles for parts that has more regular shape, right? And you can subdivide these elements into finer and finer elements, so you have more detailed modeling of how the stress will be distributed in this irregular shape, right? So having seen all this example, we can sort of briefly summarize what are the advantage of finite element analysis before we move on, right? So as you can see, the finite element analysis are trying to deal with systems with irregular boundaries, right? The boundaries that are not triangle, not square, not rectangle, but very arbitrary, right? It will be used to understand the response of your structure when it is put under a general loading, right? It can be used to different materials that ultimately just determine the K value, the force constant or the spring constant in the material. So that's the bit that's actually material specific, right? You will have boundary conditions, for example, at which point of your structure you are putting the load, and you will have, for example, if you build a bridge, right, there will be anchoring point where the bridge is anchored to the ground, and those are the points where the structure are not supposed to move at all, right? Those will be your boundary conditions building into your design, right? So when you fix certain part, when you're not allowed to move, how will affect the overall force distribution. It also gives you the ability to choose a variable element size, right? You can choose a coarser or bigger element, right? That give you less equations and which allow you to solve the equations much faster to get a general overview of how the system will behave. Once you got some general idea, you can start to refine the elements to use smaller and smaller elements to get detailed understanding, especially at the part where the structure is suffering from a lot of loading, right? Potentially will collapse. So you want to model those parts very accurately with smaller and smaller element size. So that makes the whole thing easily modifiable, and it's dynamic, so you can change how this thing behave, how the finite element evolve as we want to get more and more detail into the problem. Linear or non-linear problems, either in geometry or material. What does that mean? It means that if you look at your stress strain curve, from first year mechanical property courses, initially the loading with respect to deformation is linear, right? That's the part where you can work out the Young's modulus. That's the part you can work out with finite element analysis, which will be covered in this course. But you know that after the yield point, the material starts to deform plastically, right? So the curve is no longer linear. The stress strain curve starts to bend. So in that case, you introduce non-linearity into the problem, right? You can still solve for those problems using finite element analysis, but that makes things a lot more complicated, and we are not going to cover those aspects in this course.